Welcome back to Chapter 6. We will do the next section, 6.3, which is exponential functions. This is a nonlinear function. It's written in this form where we have x as an exponent. Compare that to when we did linear. Linear would be something like y equals mx plus b. This is a different format and results in a different graph that we'll get into in this section. First, as a reminder, linear functions are adding and subtracting the same number each time. That's their pattern. If we look at exponential, they are multiplying and dividing by the same number each time. So we should be able to tell whether this table represents linear, exponential, just by looking for the patterns. So here we can see our x's are increasing steadily on both, so that's no issues. So let's look at the y values. It's going, let's see here, up by 2, add 2, add 2. They keep adding 2 consistently, so this would be linear. This one, well, they could be adding 4, adding 8, adding 16, but that's not consistent, so it's definitely not linear. Another pattern could be that they're multiplying by 2, multiplying by 2, multiplying by 2, which would make it exponential. If we try that again, once again, we can see the x's. I know this is skipping some numbers, but it is steadily increasing by the same rate, so we're okay. They're not jumping around. Let's see, 8 to 4, 2, let's see, they could minus 4, minus 2, minus 1, but that's not consistent. How about they're dividing by 2, or in other words, multiplying by a half? They're taking half as much, so that would be exponential. Let's see, from 1 to 0, they could, let's see here, subtract 1, subtract 1. Yep, they keep subtracting 1 consistently, so that's linear. All right. When we graph exponential functions, if b is bigger than 1, we're really looking at this blue graph here. This is would be an exponential growth function if b is bigger than 1. If you made it negative, then it would just flip it over. If that b value is between 0 and 1, something like 0.2 or 3/4 or 1/2, anything like that, then it would be decay. It would be starting big and then getting smaller. Notice how both of these have a place where they're leveling out. We'll get into that in here in just a moment. So, graph this one here and let's find the domain and the range. So just go to your graphing calculators. There is no shortcut. When we do a linear graph, then we often use the slope and the y-intercept. Here, just go to the calculator because you just need a table of values. Look at your table, plot some points, and you should get a shape like this. Notice one end doesn't just keep going down. It just kind of levels off here, and one end keeps going up, up, up. Okay. Domain is all real numbers. Always here for these types, unless we have a clear start and stop. Range is what's unique. What is going on with these graphs here is this would be exponential growth, but on this side here, it just keeps going down. If you look at your table, maybe I'll go ahead and pull up the table here so you guys can see it a little bit easier. Make sure when you're using the calculator, you type it in exactly as you see it. All right, just get our graph. Yep, that looks like what I plotted. The table. Now, as x gets bigger, the numbers keep getting bigger and bigger and bigger. As x gets smaller, as x gets more and more negative, notice what's happening to our numbers here. Let's see, we had 8, 4, 2, 1, then a half, then 0.25, then 0.125, 0.0, so on, even so far. When you see these e's, what's happening is that scientific notation, and these would be really small numbers, like 0.0009, for example. So these are so small that they're basically 0. This is leveling off towards 0. Notice how it never goes below. It never gets into the negative values. Okay, and on the table too, we never get to a negative number. There's a negative power here that means times 10 to the negative fourth, but these are not negative numbers. So what we have here is y is greater than 0. We can never reach 0. We just keep getting closer. That's the definition of an asymptote. Not something you guys have to stress over, but something we'll see here. This line here, this x-axis, represents an asymptote. It's a line that this graph is approaching but can never reach. So it would be greater than but never equal to 0. If you graph this one, go to your calculator, graph, you'll notice that you get a decay function, but this negative sign is flipping it. So we get a graph that looks like this. So it's kind of like steadily going up, and then it kind of flat lines. It levels out right here. Once again, we still have a domain that's all real numbers. This graph keeps going down, 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 down. So it's got to be y is less than. So where is it getting, less than what? Well, again, look at your table. It's getting closer, closer to 0 once again. 0 is the default until we see that our graph could be shifted like we'll see on the next example. Here we got this graph. Notice they put some more numbers in there. This H and K just represent some movements left, right, or up and down. Nothing you need to stress over. Just put the whole thing in your calculator. Make sure when you type this in, you type it in like you see it, 4 parentheses 2 close parentheses raised to the x minus 3. That minus 3 is up there with the x. But move to the right so that you can do the plus 2. The x minus 3 is up top. The plus 2 is down on the regular line here of the problem. If you graph, you should get something that looks like this. See how it's kind of like flat and level, and then it starts to get that exponential growth there. Okay. So once again, I can kind of see it here, and I can look at the table. As x gets, let me scroll back down here. As x gets bigger, my numbers just keep getting bigger and bigger and bigger over here. But as you get more negative, let's see, it's getting smaller, smaller, smaller. 3, 2.5, 2.2, 2.1. Wow, kind of like slowed down. Like, see here, basically it's getting closer and closer to 2. Okay, it's also been moved up 2 because of this graph. So our domain is still all real numbers, but the range would be everything greater, because it keeps going up, greater than 2. We don't go below 2, as you can see from the table. Okay. And here's just some more types. Just graph these as well. If you graph this one, just be careful how you type it in. You should get something like this. Domain, of course, is all real numbers. It's got to be less than because it's going down. And how about -1 in this case? It's been moved down 1. And if you look at the table, it's getting closer and closer to -1. This one is our decay function. You can see it really level out here in flat line. Domain, still all real numbers. Range got to be y is greater than, because this end keeps going up. It's actually be close to 3. If you look at the table, it's getting closer and closer to 3. So that's all there is to it. Just graph and identify domain and range. No big deal.